Welcome to iLecture Online, and our next section, section 5, has to do with the thin film. And again, the thin film is a device, is something that causes interference of light. And let me explain just a moment how that works. So let's say we have a glass, this could be a lens or this could be a window or anything like that, and we put a small thin layer of some material on there that has a different index of refraction of either the air or the glass. And let's say in our example here, the index of refraction is 1.4. What that means is that when a beam of light comes to the boundary between the air and the film, part of it will be refracted and goes into the film, part of it will be reflected. Then when you get to the other side of that boundary, again, part of the light will be refracted into the glass and part of the light will be reflected off of this boundary. And to be honest, of course, at this point, some of the light will also be reflected again, but we're going to ignore that portion of it. We're only going to take a look at the reflected light of the top of the boundary here, of the first boundary between the air and the coating, and then we're going to look at the reflected light that comes off the boundary between the coating and the glass. And when those two beams come together, they can either interfere, well, they will interfere with each other, but they can either have constructive or destructive interference. In other words, if those two beams are in phase, then you'll see constructive interference and you'll see some bright light coming back on the other side. Excuse me. If the two beams of light are out of phase, then they will destructively interfere, and essentially you could see nothing at all. So you could actually see zero light being reflected because they're destructive interference, which means then that the light will be completely transmitted. So if no light is reflected, all the light is transmitted. If light is reflected, then that particular wavelength of light is not being transmitted. An interesting thing happened to us when we were driving home from my kid's soccer game. We were driving on the freeway, and I was looking on the other side, seeing all the cars coming from the opposite direction, and the sun was shining on those cars. And what was really interesting was there was a very bright blue spot on every one of the windshields, all the way down as far as the eye could see, on every one of the cars. And I go, wow, that's exactly what's going on over here. On windshields of cars, apparently they put a very thin film, a very thin coating on the windshield that will cause blue light to be reflected from the windshields and the rest of the light to be transmitted through the windshield. And why would that be? Well, there's two advantages to that. If you reflect part of the light and allow the rest of the light to come through, you'll see a crisper, sharper image. So that means you can see very clear through the windshield because there's less of a what we would call, your eye can then better focus on the singular wavelengths that come through, as compared to all the light coming through the windshield. And secondly, it is a little bit softer on the eye because blue light is a little bit harsher to the eye than, of course, the yellows and orange and the red and so forth. And so then the image is a little bit softer to the eye, and it takes a little bit of the intensity of the light away. So all kinds of advantages. But it was kind of interesting how that worked. So here I'm going to use as an example to show you how a thin film works like that. So in this case, we have blue light being reflected and the rest of the light coming through. And let's say that the wavelength of blue light, let's say the lambda is equal to 400 nanometers. Okay, if that is the case, then how does a thin film work? Well, for one thing, you can see that there's a path length difference. The extra distance traveled by the second ray, this is the first ray, this is the second ray being reflected. You can see that it has to travel through the film and back through the film this way. And if the thickness of the film is t, then we can see that the extra distance traveled is equal to 2 times the thickness of the film. Now, for the light to be reflected, these two have to be in phase, which means that the extra distance traveled must equal a full wavelength. If they're equal to a full wavelength, then of course they will be back in phase and there'll be constructive interference. But we have to be careful here. Since the light is traveling through a coating that has an index of refraction that's different from air, the wavelength will have shrunk. It'll be a smaller wavelength, so the extra distance traveled is equal to lambda sub n, which means it's equal to the wavelength in air divided by the index of refraction of that coating. And so we're going to use n equals 1.4 in here to adjust for the wavelength. And so we can now say that if the extra distance traveled, which is equal to lambda over n, if the extra distance traveled by the second ray, which is lambda over n, is equal to twice the thickness of the film, then we'll have constructive interference. And now the question comes in, how thick do they need to make the film to make that happen? Well, we're looking for t, and so we can say that lambda is equal to 2t times n, or in this case, t is equal to lambda divided by 2n, and the wavelength we're trying to get to be reflected is going to be 400 nanometers. That's 400 times 10 to the minus 9 meters, and we divide that by 2 times n, and n of the coating is 1.4, and yep, that's it. And so where's my calculator? Here we go. So we take 400 e to the 9 minus, divide by 2, divided by 1.4. That means we have to have a coating that has a thickness of 143 nanometers. Now that's not a lot. That's a very thin coating, and you could probably look at the glass and not really see it, but it's there. They put that on there, and something like that will allow the blue light to be reflected off windshields and the rest of the light to be transmitted through the windshields. So very clever invention. Now, one more thing that I ignored, and we have to be careful. There's something else that happens at the boundary of light when it gets reflected. It's not something we have to worry about when it's transmitted or refracted, but when it's reflected, something may happen to the light. When light bounces off a boundary or reflects off a boundary, where the index of refraction on the other side of the boundary is greater than the index of refraction where it came from, then light will actually have a phase shift, an instantaneous shift of 180 degrees. So here I'm going to put the letter yes, or Y for yes, because yes, there is a phase shift here because we go from 1 to 1.4, which means the light, as it's reflected, is already 180 degrees different from what it was when it bounced off the interface. On the second interface, we also have a condition where the index of refraction on the other side, without for a glass, is greater than the index of refraction of the coating. So there's going to be a phase shift as well. And if there's a phase shift at both boundaries, then we can simply ignore it and follow this rule and nothing has happened. But what if one of these has no phase shift and the other one does? That means the two rays already are 180 degrees out of phase without having to travel an extra distance. And there's going to be an example next when we continue with this topic on how to deal with it when these two are not the same. So before you complete the problem, before you figure out what the thickness of the coating should be, always take a look and make sure that there's, whether or not there are phase differences caused by the reflection of the light, if the index of refraction is greater on the other side compared to where you came from. So if it's yes here and yes there, or if it's no here and no there, then you don't need to worry about it like in this particular example. But if it's yes here and no, or no and yes, if they're different, then you do have to take into account. In the next example, we'll show you how to do that.